Okay, YouTube, this is my second video on the transformation of quadratic functions, in which we're going to continue our exploration of quadratic functions that happen to be written in this form: a times the quantity x minus h quantity squared plus k. And what we're going to focus on in this video are not so much translations, which, as we saw in the last video, h is responsible for left and right shift, k is responsible for up and down shift. But what we're going to do is we're going to focus on the value of this a out in front and tie it into these transformations that we've seen with functions in the past. So we'll start with our reflections here. Recall that given some parent function, this is f of x is equal to x squared. If you were to take some graph here, which is that f of x equals x squared is our parent function here, and make all of its y values have the opposite value of what they currently have, what's going to happen is that you're going to cause it to flip over the x-axis or cause an x-axis reflection. So essentially, by taking this f of x and making all of its y values, because f of x means the same thing as y, make it negative, then you're going to cause an x-axis reflection. And if over here we were to look at this and say, given some f of x equals x squared, if you were to make all the x values negative, it actually would reflect over the y-axis, which I think is important to note. Y equals x squared is its own reflection in the x-axis. It would reflect onto itself given that parent function if you were to reflect it over x. So what I want to do is talk about the impact on the value of a when it's in this form. And essentially the impact we have here is this. If we were to find negative f of x, well, negative f of x is really negative this x squared thing, and negative x squared is negative the x squared thing. So what we can say is if you have a negative out in front, right here in front of this parentheses or in front of your squared term, what you know is that you have a parabola that I'm just going to say it opens downward. It is reflected over x, but it opens downward. And if you were to say now plug in a negative x into this function, well, I know that x squared is my rule. So whatever I'm plugging in, I'll square it. And when you square this negative x, it's actually negative x times negative x is a positive x squared. So you actually get the same thing as what the parent function is in the first place, and that's why it actually, when you reflect it over the y-axis, you get back the same rule you started with. So we're not going to worry so much about the negative there as much as we are going to worry about the negative being out front. So if you have a negative for an a value here, if a is negative, then it opens downward. We say if a is less than 0, then it opens downward. Okay, so now, stretching and shrinking, what we've known in the past is given some parent function, of course we're looking at the quadratic parent function f of x equals x squared, we know that if we want a horizontal stretch or a shrink, then we need to multiply our x values by some quantity, or some constant a. So what you see here, and hopefully you can see this, is f of a times x. And what we need to remember about horizontal stretch and shrink is that if a is greater than 1, okay, if a is greater than 1, okay, then what you're going to get is this blue graph compared to the black parent function graph, which means that a greater than 1, if you're multiplying by the x values, is actually shrink. So we say horizontal shrink toward the y-axis when a is greater than 1, but if a is between 0 and 1, if it's a proper fraction, then we're going to get horizontal stretch or away from the y-axis. Okay, so that's this red graph here if a is somewhere between and not including 0 and 1. So vertical stretching and shrinking, we'll talk about the impact on our function here. If we were to say, well, now take all your y values, f of x, times some value a, then what you're going to end up with is this. Well, a times f of x is equal to a x squared. And you'll notice that that's that number that's written out front here, just that a. And so if a is greater than 1, okay, then we're going to get vertical stretch away from the x-axis, where if a is some proper fraction here, in this y equals ax squared expression, we're actually going to stretch this out, and that's what's listed down here, okay? So what we're going to do is essentially, for these three transformations, describe what the transformation is from the parent function, f of x equals x squared, that is represented by g. Then we're going to sketch the function very quickly, as a matter of fact, and then lastly, we're going to state the domain of range. So what I want everybody to notice here is this. In terms of a, h, and k, I'm going to rewrite this very explicitly, but we technically could write this as a, which is negative a half, it's our value or coefficient of our x squared term, times x minus, well, this would have to be a 0 if there's nothing in here, and then this would also have to be a 0 out here. So to sketch this function, really the three values we're looking at are a, h, and k. And the first thing I notice is that h and k being 0 and 0 cause my graph to translate nowhere. It would be the same as our parent function, except for our a value is not equal to 1, as it is in this f of x equals x squared. It has an a value of 1. So looking at the a value now, the first thing I notice is the fact that it happens to be negative. So the first thing I want to indicate is that given our parent function, which looks like this, opens upward, to make all of that negative, all the y values negative, what that's going to cause to have happen is it's going to open downward. And also the fact is that we're multiplying by a half out in front. We're not taking the x values times this, the a value out in front. So here's the trick to it. We say, well, usually my function goes up 1, right 1. If I were to take all these y values times a half, it would only go up a half and right 1. And since this opens downward, what we're going to do is we're going to say it's reflected over, and it's going to go down a half, right 1. So you can see that this is going to be a little bit wider, and because all parabolas have symmetry, we'll go down a half, left 1. But what you're going to get, in again, this was normally at a height of 4, this would be at a height of 2 now. This parent function at 2 would be at a height of 4, now it's going to be half of that. But you can see that we're going to get this parabola that is slightly more vertically shrunken, okay? So we say vertical, vert shrink by factor of a half. That's what's this a value has caused to happen. We also have an x-axis reflection. So looking at the purple graph here, well, one thing we can say about all three of these graphs we're about to sketch is that the domain is all real x values. And the reason why is because since these graphs go left and right forever and ever, every x value will have a y value that it maps onto. In other words, all the numbers on the x-axis will be plugged into this function. So I can copy and paste that here, and I can copy and paste that here. As far as the range goes, though, maybe I can switch over to like a brighter color here, green or something. I noticed that we only hit y values that are 0 or less on this function on the y-axis. So we would say the range of this function is all y values less than or equal to 0, and the reason why it's less than this time is because, well, it opens downward. So looking at this next function here, one thing I do want to point out is that we have 2x squared minus 2. So our k value is this value out here. You notice that we don't have an h value on the inside of the parentheses with our x. So it's not going to be shifted left and right at all, but our k value is actually negative 2. So this function, when quickly sketched, we would indicate that it just starts down 2. And what you see here is this 2x squared. Technically, this a value is being multiplied by the x values. And what we know about this is when you multiply the x values times some constant, that you're going to get some horizontal stretch or shrink. And the fact that a is greater than 1, okay, would indicate that we're actually going to get a shrink here in towards the y-axis. What I'm going to do is give a suggestion, and it's this. If you say have a constant times your x values in here, 2x is what we have here, what you could really do is just go ahead and square that. And what you get is 2x times 2x is 4x squared. So another way to write this function would just be 4x squared minus, well, not minus 1, minus 2. But the point is, I want you to see that we could always interpret horizontal shrink and stretch as some form of a vertical stretch or shrink. And I can easily see that this is a vertical stretch since we're taking the out in front here, the x squared term times some constant a. And because a is greater than 1, it's going to be stretch, and it's going to be by a factor of 4. So instead of going up 1, right 1, it's going to go up 1, 2, 3, 4, right 1. And because it has symmetry, we know it goes up 4, left 1. And this graph is going to be really, really vertically stretched here. So we would say that this g of x here has a domain of all real x values, and it seems to me that it covers all y values greater than or equal to this one right here, which would be y greater than or equal to a negative 2. So lastly, taking a look at this function, we can see that there's a difference between k values and h values. I hope you notice this. The k values are not in this quantity, in this squared quantity with our x values. K values are always on the outside. I'll call those loose terms, whereas this one's here is kind of captured by our x. So we say we have an h value here, and I'm going to point this out. H is actually positive 1. And our a value in this case, I observe, is positive 3. So things I can tell about this graph instantly are that it's shifted right 1. It's going to be shifted right 1 from the origin. And also this, because our a value is positive, it's going to open upward. And lastly, because a is greater than 1, not only is it going to stretch away from the x-axis, it's going to stretch by a factor of 3. So right 1, up 3, or up 3, right 1, instead of up 1, right 1. It's going to be triple that original height. We say it's not as stretched as the last one we did where we had quadrupling of the y values, but still the same kind of idea. So we say the range of this here would be all y values greater than or equal to 0, since those are the y values on the y-axis that are covered by this function. Cheers.